Hello and welcome back to Calculus 1, section 4.3 on first and second derivative test, or whatever ridiculous title your book has. So we are going to learn about functions in terms of increasing, decreasing, concavity, and all of these things that we analyze, stuff that we need for the work. For instance, if I have a curve, let's say it goes straight like that, then falls, then goes up like that. Let's say this is it. And that's f of x. I can immediately see that the function is constant over here, it's decreasing over here, is increasing here. And now all of that happens along the x-axis with some intervals. So let's call this x1, let's call this x2. We have negative infinity and positive infinity. Looking at this graph, right, just using eyes, we can say that from negative infinity to x1, function is f of x is constant. Then from x1 to x2, f of x is decreasing. And from x2 to positive infinity, f of x is increasing. And what's important is that all of these here are intervals, not points. Intervals. Interval on x-axis from x1 to x2, from A to B. Intervals, right, on x-axis. So if you are supposed to provide an answer on the decrease of a stock market graph, right? By the way, if you ever wondered why stock market does this, it's just simulating heart attack all the time. That's technically what it is. Now, what you have on the x-axis is time, right? You have time. And on the y-axis, you have money. So if you are looking at the stock market graph, it is safe to say for this one that the money is being lost, right? If you just shoot this a linear line through it, approximated, right? There's a little dip over there, but it's fine. We see decrease, right? So we're losing money. We can take a look. If this is, let's say, a day or a year or whatever period of time, we have money that we started with and money that we ended up with, and it's about half of the value, right? So if this is, let's say, a year of a stock and it's, let's say, gone from $100 to $50, then you are losing $50 per share. You have 100,000 shares. That's a lot of money, right? 100,000 times 50 is $5 million lost, exactly. So should have paid attention and sold, right? Before you lost 5 mil. So we want to know if the function is decreasing, if the function is increasing, if the function is constant. Obviously not just for stock market, but also for all of the other other things. So now, let's take a look at what we call the first derivative test, which will teach us about the way to find increase and decrease using calculation rather than, staring at the graph. So, first derivative test, also known as FDT. And we have these two. So if f prime of some value a is less than 0, actually let's use c, sorry. If f prime of c is less than 0 on some interval a to b, then f of x is decreasing on a to b. So if the first derivative is less than 0, now you already know this from before, right? We graphed the function and the derivative. And the second one is that if f prime of c is larger than 0 on AB, then f of x is increasing on AB. And finally, number 3, if f prime of c is equal to 0, you have a critical point, which could be min, which could be max, which could be also inflection point. We'll get to it. So this is your first derivative test. And clearly, calculation and you get a number, it can be only one of these three. Equal to 0, less than 0, then more than 0. Right? There's no fourth option. Now, does this make sense on a graph? Well, you just need to recall the old stuff, right? So you have some kind of f of x on xy graph, and we are going to have these horizontal tangencies. We know this from before, where slope is 0. And these happen to be your max and your min in this case, both relative in this case. And now I have the function being increasing over here, decreasing, and then increasing again. And that happens on these intervals, right, from negative infinity to, let's say, a, and then from a to b, and then from b to positive infinity. So we can quickly, now why is that so? Well, increasing function, that means that your slope of the tangent lines, all of the tangent lines, is larger than 0, which is the derivative is larger than 0. Then we have our slopes less than 0, and in this case we have slopes larger than 0 again. So these are the things that we already know from before, and now we'll just put this in one concept, right? Call it first derivative test, and we use this first derivative test to locate min, max, intervals of increase, intervals of decrease. So everything is on a pile. So first one, we are going to test this out on x squared and 1 over x, and then we'll go and take some homework examples before we move to second derivative test. So let's test this first derivative test on f of x equals x squared. And in order for me to get this working, I'll first take the derivative and set it equal to 0 to find my critical point, well, critical number. And we are using this because we actually don't know what the graph looks like. We just want to find the important regions. So what do? I partition my domain, which is from negative infinity to positive infinity on x, right? I partition my domain using this critical point, and then I pick two test points. Now, guys, those are your C's from the theorem up there. So now, So now I'm doing my first derivative test, which is f prime of -1. You use f prime equation, which is 2 times -1, which is -2. That's less than 0, implying that the function f of x is decreasing. So we'll put a decreasing arrow. And then I will test the second point in the derivative, which is 2 times 1. Get 2, which is larger than 0, which means that the function f of x is increasing. So I'm done. I already discovered, and all I need to do now is to write the answer. What's the answer? F of x is decreasing on negative infinity to 0. F of x is increasing on 0 to infinity. This is my answer. This is what you have to put down if you want the points on the test. Because this is actually what your report is going to have when you are giving the report. Right? You are losing money, you are gaining money. Right? And provided the times, right? Now, can you tell me what else do we get for free? We did all of this analysis. This is your first derivative test. We're done. What else do we get for free? No, that's going to be second derivative test. The increase and decrease cannot give us concavity, and I'll explain why. But there is something else that we get for free. Yes. By looking at that diagram over there, what we get for free is that we have a minimum at x equals 0. Because you see that the arrow goes down and the arrow goes up, right? You know, they say you hit the bottom. When you hit the bottom, you bounce up, right? So we see that the function is decreasing, and then it's going to hit the 0, and then it's going to bounce up and increase, so that means at 0 there is a minimum. You can go and calculate the y value. But this first derivative test is awesome because it spells out all min and max values. We do not have to go and do the test points later on because it's already done. It's great. One more example before we go into these spicier cases. How about f of x is equal to 1 over x? Same drill. We are going to find the derivative, which is -1 over x squared. We are going to set that equal to 0, and find that -1 is not the same as 0, so no solution. If there is no solution, that means no crit number, which means no crit point, which means no min max. And we are okay. Some functions do not have min and max. So you follow this logic because the function had no solution, then that means that we don't have a critical number, then critical point, and then we don't have min and max. That's fine, right? But now what do we do for the first derivative test? Well, this example is going to give us a second part of the story, which is that partitioning can also be done with vertical asymptotes. There is a vertical asymptote. Let me write that in blood. There is a vertical asymptote at x equals 0. We use that for partition. So now my negative infinity to positive infinity x domain is again partitioned at 0 because that's where the vertical asymptote is. And I am picking two test points. We'll use again -1 and 1. And now we're going to run the first derivative test for -1. Well, that's 1 over -1 squared, which is 1, which is larger than 0, which tells us that the function is increasing. And we are going to put the increase right there. And then we have f prime of 1. Oh, wait, guys, this is a negative 1 over x squared. There we go. I was wondering what's wrong. And now I have -1 over +1 squared, which is still -1, which is still less than 0, which is still decreasing. So both are decreasing. Do we see that we do not have a change to have a min or a max? Right? There's no change. So it's decrease, decrease. And answer, because you might want your points, you will say f of x is decreasing on negative infinity to 0, union 0 to positive infinity, right? We have to break it at 0 because of the vertical asymptote. And that's the answer. No min, no max, no critical points. And I just hope that you know what the graph of 1 over x looks like so that you can see that the function is always decreasing. From negative infinity to positive infinity, function is always decreasing in the case of 1 over x. And we have a 0. So decrease from 0 to from negative infinity to 0, and then from 0 to positive infinity, another decrease. So 1 over x is always decreasing, except it has that hiccup at 0, right, of the vertical asymptote. So it goes decrease, decrease, and then decrease, decrease, decrease. That's that. So now they have few exercises for you to enjoy on homework. And when I say few, I mean 20. Exactly. So let's see what is the sum of the stuff that... Let's go easy. All right? Easy. 27 says f of x is equal to negative x to the 4 over 4 plus x cubed minus x squared. You know what to do. Take the derivative, set it equal to 0.
You can use the quadratic equation, quadratic formula, I mean.
or whatever else works. I mean, factoring one essential oils, I don't know. Oh. Lately, essential oils have been answer to everything. So, when you run into a quadratic equation, maybe it works. I don't know. I'm starting to the problem, see how it goes. You've seen that meme with the 3 cups and 2 Bellevue trying to break through the door?
Yeah, I think I have.
Each one has one is polio, one is measles, one is something, right? And on the other side, the door says non-vaccinated kid, right? And the other side is a noodle holding says essential oils on it. These guys, it's one of the funniest things.
You know the new risk of like.
No.
I feel like it's a kind of like a. So I don't know if you do it, but like you didn't like Fortnite kind of cartoon. This is used to be a 2D platform. Now it's going to the 3D. It's a dungeon kind of crawler. Has a certain like 4 or 5 different dungeons that you have. So it's multiplayer or single player. It's just you get a bunch of items that level you, like pretty much give you certain abilities.
Standard out, you just say.
Like that.
Alright, we'll talk.
Early access.
We'll figure it out. Alright, what do we have over here? F prime is negative x cubed plus 3x squared minus 2x. Now we need equal to 0. We will factor out negative x, left with x squared minus 3x plus 2 equal to 0. This one factors into x minus 3. No, I lied. X minus 2, x minus 1, right? So when I set each one of these equal to 0, using the 0 product rule, we have x is equal to 0, x is equal to 2, and x is equal to 1. Those are our 3. And now we use these to partition the entire domain. So partition at 0, partition at 1, partition at 2. And this is my positive infinity this way, negative infinity this way, right? This is x-axis. So now I need test points. I will use negative 1, 1/2, 3/2, and 3. So in red, test points. And now we get to do the first derivative test using all of the test points one by one. First derivative computed at negative 1. So we go to the first derivative. So it's negative 1 cubed plus 3 negative 1 squared minus 2 times negative 1. And we calculate this. So this is 1 plus 3 plus 2 is 6, larger than 0, increase. Then we have the half. F prime of a half. That's negative 1/2 cubed plus 3 times 1/2 squared minus 2 times 1/2 is equal to what? Well, it's negative 1/8 plus 3/4 minus 1. Now, it's less than 0. We don't have to compute. If you already see it's less than 0, you can just, because these two, right? 3/4 is smaller than -1, and then -h is going to make it more negative. So it's equal to a number, but it's going to be less than 0, so decrease with the arrow going down. The next one is 3/2. F prime of 3/2. So we have -3/2 cubed plus 3 times 3/2 squared minus 2 times 3/2. These guys cancel. I have 27/8 negative plus 27/4 and minus 3. Now, so these guys combine immediately, right, because they're just half of each other, right? So this is 27/8 minus, and then 3 times 8, 24/8, so it's positive increase. The secret is that anytime you have a polynomial, they have to alternate. Up, down, up, down. When you have a polynomial, for anything else, by sine and cosine, sure. But for anything else, it can go, either way. So now we had another increase, and then the last we are checking number 3. So f prime of 3, which is -3 cubed plus 3 times 3 squared minus 2 times 3, and that's clearly less than 0 because these guys cancel. So this is -6, which is less than 0, so decrease. All right. You got a lot of partial credit so far, right? What is the answer? Remember what we are looking for. We are looking for intervals of increase and decrease. So you will say f of x is increasing on, and you will go and find the increase. -∞ to 0, union 1 to 2. So this is where the arrow goes up. And then f of x is decreasing on 0 to 1, union 2 to infinity. And that's the answer. You specifying exactly the intervals at which this is happening. What do you get for free? You get all of the min and max values, right? You go up to the graph, and you say maximum at 0 and at 2, and the minimum at 1. So that's free. Here, I'll add this. It's one of those deals. And if you call in next 15 minutes, you will get right, but you don't have to because it's already there. So you just look at it, right? So max values at x equals 0 and 2. And minimum x equals 1. Now you have to go and calculate y values, right? If the question asks you to find points, these are not points. These are just x values, right? You will have to go and plug these in the original problem and figure out the y values. So let me put that in blood over here. Need all y values, which means plug in original equation and calculate those y values. All right, so that's a warm-up problem. A little bit of factoring and so on. Let's do something more interesting over here. lock the doors? No one is leaving. F of x is equal to square root of 2 sine x minus x on interval 0 to 2 pi. Just a little bit of trick to for the good measure. So take the derivative, and then you have to solve trigonometric equation. You get to keep all of the answers that are between 0 and 2 pi, because you know that trig equations have infinitely many answers. Just have to keep the ones that you care about. Okay, let's take a look at this one together. So the derivative f prime would be, copy the constant, derivative sign is cosine x minus 1, and we equal it to 0. So this will be cosine x is equal to 1 over root 2. And if you multiply by root 2 to rationalize, you will get the equation cosine x is equal to square root of 2 over 2. Now, that happens at pi over 4. Now, we need a unit circle. All students take calculus. I don't know if you did that way. 45 degrees is here for the positive cosine. So we have that x is equal to pi over 4. And another positive cosine is in the fourth quadrant, which would be 7 pi over 4. So these are the two values for our partition. So I have, now my partition starts at 0, and adds the 2 pi, because I have the interval that cuts it off, right, from the infinities. So it's my pi over 4, and this is my 7 pi over 4. So now I get to pick test points. Now, what are the cool test points? Well, we can't really compute these pi over 8 or something. Well, we can have a pi over here, that's great. All right, as a test point. Picking 7 pi over 8 and pi over 8. Not that great, right? But such is life. Let's see what we can compute. F prime, let's compute pi first. So f prime of pi, that's a square root of 2 times cosine of pi. Square root of 2 times cosine of pi minus 1. Cosine of pi is? Very good. So you have root 2 times negative 1 minus 1. Do we all agree that this is less than 0 without calculating anything, because you have a negative minus a number? Right? You have a positive times a negative. That together is a negative number, and then you're subtracting 1. So it has to be negative. So we definitely have a decrease on that one. Now, what are we going to do for pi over 8? Square root of 2 cosine of pi over 8 minus 1.
Why couldn't you use pi over 6? Yeah, for 36.
Who said we can't? No one said we can't. I was about to pull out some formulas, but that's okay. That's okay. We'll do pi over 6. Your happiness is our primary concern.
Let's do pi over 8.
7 pi over 6. Does that work over there? It works. Okay. What's cosine of pi over 6? Very good. Minus 1. So this is definitely going to be 6. That's 2, 1. Yes. So this is definitely larger than 0, because you have root 6 over 2 minus 1. That's larger than 0, so it's increase. 7 pi over 6 in a cosine is going to give us the same answer. 7 pi over 6, same. Great. Well, answer. F of x is increasing on 0 to pi over 4 union 7 pi over 4 to pi. F of x is decreasing on pi over 4 to 7 pi over 4. Note my use of parentheses and brackets and stuff. I have a closed interval, 0 to 2 pi, so those values are included, as right infinity is not included. I think we already went through that exercise in class. Who's the only person who will count to infinity? There we go, beautiful. Paying attention in class. Important stuff. Yes, Chuck Norris is the only one who can count to infinity. Twice. In 5 minutes. All right. Next, min max, we can do that. That's all free, right? So minimum at x equals 7 pi over 4. And then max at pi over 4. get y values. Good. Now, as if that wasn't spicy enough, one more wonderful problem before we switch to the second derivative test, and this will be x squared ln x squared plus 1. So the derivative and stuff set it equal to 0, solve the equation of the vacuum. All right, so step number 1. You see this 2 over here? We make it disappear. So we don't have to deal with chain rule, at least. So this is equal to 2x squared ln x plus 1. Now that makes things f prime. Please make all of the face palms crisp. None of that dull stuff. So now, copy the first, which is 2x squared. The derivative of the second is 1 over x, plus copy the second, which is ln x, times the derivative of the first, which is 4x. Now, these cancel. F prime of x is equal to, I have 2x plus 4x ln x equal to 0. Factor out 2x, 1 plus 2 ln x equal to 0. And then I have 2x equal to 0 and 1 plus 2 ln x equal to 0. Well, the first one is x equals 0, and that's a nice one. The other one is ln x equals to negative 1/2. Bueno? Yes, we can e both sides. I was wondering if everyone is with me. So this is e to the negative 1/2 or 1 over root e. Great. I got 2 critical points. I mean numbers. So we can partition. Now, what else do I know about my function, though? Nice one. No, it was a quality sneeze. I approve.
It's a logarithmic function.
Yes, and logarithmic function has what? Excellent. At 0. Great. Teeth pulling was successful. I should have been dentist. So this thing has a vertical asymptote at x equals 0, and that's important because we are going to partition. Now, luckily we have x equals 0, so partition, right? But it's not always that's going to line up that nicely. So I have my partition at 0, and I have another partition at 1 over root e. And there is a negative infinity and there is a positive infinity. You have to be also careful if the domain allows for negative infinity to positive infinity. You see, the trick is that you had ln x squared. And because you had ln x squared, it allows for positive and negative numbers. We hopefully all know that the ln graph is only one side, right? The domain is 0 to infinity, in which case you would have to can this side. But because it's x squared and squares kill negative, right? Then we actually have this situation. So it's only a vertical asymptote that is a problem. Good. So these are our partitions, and now we're going to choose values. Right? Negative 1 is a good value. Since we have ln to calculate, then definitely e is a value. Now, what could we choose in here? Can we choose one?
Well, to be safe,
one half.
yeah.
Yeah, but then I have to calculate ln of 1/2. 1 over, I already like it. E squared. Would you all agree that e squared is bigger than root e?
Yes.
right? It's square root of x and x squared. Which one is bigger? X squared is bigger, right? But then if I put 1 over, which one is bigger now? Well, this one is bigger, right? So that's the trick, right? We pick something that has e's inside too. Do you have, no, you just punch the decimals and you can put anything in the calculator, who cares? But can we do 1e or, oh yes, 1 over e would work. You're right. Yeah. Be all dramatic. E squared. E to the 7th power. Because we can. So f prime of -1. First derivative test. All right, let's plug in -1 into our derivative. And we see an issue immediately, right? Because we have 2 times -1. And then 1 plus 2 times ln of -1. And no solution. So we eventually actually end up canning this part. All right, fine. F prime of 1 over e. 2 times 1 over e. 1 plus 2 ln of 1 over e. This is 2 over e. 1 plus 2 times of ln of e to the -1. So now ln e to the -1 jumps in front, ln e is 1, so we just have 2 over e, 1 minus 2, and the whole thing is -2 over e, which is less than 0. We have a decrease. And now we do the same calculation for e. 2 times e, 1 plus 2 times ln e, which is 2e. And this is times 3, right? So answer, f of x is increasing on where? 1 over root e to infinity. F of x is decreasing on 0 to 1 over root e. This is our answer for increase decrease. And then free, we have a minimum at x equal 1 over root t. Get y. F of 1 over root t, right? Original function. That's the first derivative test. First derivative test uses the first derivative, look at the title, to determine the intervals of increase and decrease, and in the process it gives us for free which values, which critical points are min, which are max. Second part of this lesson is the second derivative test, which deals with the second derivative and concavity. Very good. I love it. Second derivative test, also known the SDT. And now this one deals with a concept called concavity. Now first we need to understand concavity as a concept. So now I am going to create 3 portfolios that over time are dealing with money, right? The graphs. So these are the 3 graphs. They all have time on x-axis because the money, which is on the y-axis, will be changing in time. So money versus time. They will all start at $100 invested. And now they will change this way. If I am, as a financial advisor, presenting you with these three options to invest your money, where are you going to invest? Option 1, option 2, option 3, and why?
Last one, because it looks like it's going to infinity.
Aren't they all?
Oh, like
Exponential.
Okay, which ones are increasing? Which ones are going to increase your money?
First and fourth.
all of them.
Oh,
All of them. Good. They're all increasing, right? Great. So, are you going to pick a dart now? Just like that one. Or you're going to make an argument and say, no, I want this one. Because this one, why? We said third one as well.
I have a question.
But the increase is not the answer because they're all increased.
But I was
Increasing faster, yes.
But does that one have, the third one, does that have vertical axis?
No.
Oh,
No
just
vertical
the draw? Oh, then I'll accept.
So now we all want the third one, right? Why do we want the third one? Well, the answer is concavity. Third one is actually concave up. That's the name for this type of a curve. Now, looking at the first one, concave down. So that's the concavity. And the one over here has no concavity, which is just a constant increase. Now, why is the third one better than the first one or the second? Since they all started the same, they all are making money. Now, what's happening here is it starts making money sluggish, but then it takes off, and this is going to go what we call exponential growth.
Looks like a bubble.
This over here is the square root. Do you see how it's slowing down in time? So if I could graph this one over that one, it would look like this, right? And at that point, they will go like, right? So this, the third one over time will make insanely more than either of the other two options. And we see that through the concept of concavity. So what is this concavity? It's just the shape of the curve that is determined through the second derivative, and something that it looks like, let's go red. Something that looks like this is called concave up, and something that looks like this is called concave down. Now also there are pieces as well. So if I have these guys, that's concave, and then these guys as well. Now these look like smiley faces. So so concave up and concave down. Now, I said how fast is the increase, right? So we know that the second derivative is the first derivative of the first derivative, right? Second derivative is the first derivative of the first derivative. Third derivative is the first derivative of the second derivative, and so on. So you are taking a derivative, right, as you progress. So if the first one is measuring the change of the function, then the second derivative is measuring the change of the first derivative. So now we see that all of these are increasing, but now the question is how fast are they increasing? And that's what the second derivative tells us. Now this one is increasing fast, this one is increasing extremely slow, and this one is in the middle with a constant increase. All right, now is the time for us to put the second derivative test. And it's the same as the first derivative, just a different conclusion, right? So if f double prime at c is less than 0 on a to b, then f of x is concave down on AB. If second derivative computed at C is larger than 0 on interval AB, AB. If f double prime of C equals to 0, then x equals c is an inflection point. Now, what is inflection point? Change in concavity. Thank you. So change in concavity. Just like the maximum, right, is a change in increase or decrease. What do? You increase, increase, decrease, you reach a maximum, then down, right? Minimum, you decrease, 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 you hit the bottom, you bounce out. So min and max, change, increase, decrease, inflection point changes concavity, and this is that third point that we said that you sometimes detect with a first derivative test, and you don't know what it is because it's not min, it's not max. Right, well now the puzzle is complete. We have all the pieces. So x cubed, as we've seen in our min-max, I think I wrote the x cubed in, right, just to make you guys aware. I should have. I haven't. Not happy. Maybe I put it on a board or something. Anyway. The first example will be, I was about to copy the whole thing, but here it is, x cubed, right? So if you do your first derivative, because you have to start there, it's called f of x, whatever, y is fine. F prime of x is going to be 3x squared, and if you set that equal to 0, you will get x equals 0. Now you know it's not a min or a max, right? Not min max. So what do we do now? Well, we find the second derivative, and that's 6x, and now set that equal to 0, we get x equal to 0, and that's the inflection point. So what we have is a partition at 0, the test points at -1 and 1, and the second derivative test using the second derivative, 6 times -1 is -6. So now we have a concave down because -6 is less than 0. That's concave down. And second derivative computed at 1 is 6 times 1, which is 6, which is larger than 0, which is concave up. Now, if you are to, well, let's first write the answer. F of x is concave up on 0 to infinity. F of x is concave down on -infinity to 0. This is the answer that you are providing for, I mean, if let's say you care about the points on the test, right? So you would, right, if you care, you put this on. If you don't care, don't worry about it. Not dramatic enough? Fine. And now I just want to draw the cube graph for us to see that at this 0, which I labeled as inflection point, my look at the screen. My concave down. You see the concave down piece? Concave down changes into a concave up. And that's what happens at the 0. So the half pieces, yes, this is concave down, but this is also concave down, and this is also concave down. So these are the three, right? You have a full concave down piece and then 2 half concave down pieces. And this is what we have now, concave, 1 half concave down and 1 half concave up. It's the same stuff as for min and max. You have to partition at inflection points and you have to partition and vertical asymptotes. Let me write that in blood. We partition on inflection points and vertical asymptotes. So that way we all know. Okay, let's take a look at some of your favorite problems. Second derivative test means take the second derivative, set equal to 0, get inflection points, do the test, and then go for a lunch. We partition on inflection points and vertical asymptotes. So you guys might want to go to the first partition you did for the first derivative test and say we partition on critical points and vertical asymptotes. The first problem was x squared, I believe. There it is. So here we partition at critical numbers and vertical asymptotes. Put that in a bubble. There we go. Make it extra ugly. Good. Yes.
What if from the first derivative, what if they are?
Then they're not going to be inflection. You can't have, right?
Use automatically, yeah. Okay.
Yes. What happens if you have no critical points, no inflection points, no vertical asymptote? What do? You have nothing. I take e to the x. It's not going to give you anything. Or linear equation, so sure. So what do you do? If you do the first derivative test, you get nothing. You do the second derivative test, you get nothing. What do you do for partition? No critical points, no inflection points, no vertical asymptotes. E to the x fits it. What do for partition? The whole partition is just one piece. Pick any number in a domain. That's usually, so 1 year, I said, you know what, I just put e to the x on the test. Everyone knows what the graph looks like. It's just going to be quick for the first, second derivative test. Barely anyone got anything done because everyone started freaking out. I have no critical points, I have no inflection points, I have no vertical asymptotes, I can't do partitioning, I can't do the tests. Right? And I have students, more than half left it blank. Right? Well, if you have nothing to partition on, the whole thing is one partition, right? If there's nothing to partition. So what are the things that are partitioning? Critical numbers, critical points, inflection points, and vertical asymptotes. If you don't have any of those, then your entire domain is one partition. Pick one number that it's easy to compute anywhere, and just go with that. And if you want to practice the example, just try e to the x on its own. Now, let's take a look at something that you will enjoy. Like problem 84 looks disgusting enough. Say f of x is equal to e to the x divided by x plus 1.
what? Sorry? Ln of 0 is 0 is yeah. Yes. Oh yeah, negative 1 and 1. And it's 1 really. You know.
Okay. Shall we? So, the first derivative, I can use the quotient, we can also use logarithmic. So, x plus 1 squared, x plus 1, then e to the x minus e to the x times 1. Now we can kick out e to the x in front, and then have over here, what do I have? I have just x over x plus 1 squared, right? Now, we also know that there is the vertical asymptote. This is the important in the beginning. X equals negative 1 is the vertical asymptote. Start there, because that's going to be in your partition. You always have to look at the original problem and make sure that you collected all of your vertical asymptotes. If there are ambiguities, you have to do the limit, right? So now, I'll put the e to the x back on top. Now it's annoying to do the quotient rule because we have a product rule and then we have a chain rule. So now we're going to use, right, logarithmic because boss, right? So we copy the function as is, and now we take the derivative, so it's 1 over x plus, and now see ln of e to the x is equal to x. So there's no ln there, so the derivative is just 1. If you have e to the x, the derivative is just 1 in logarithmic differentiation. And minus 2 times x plus 1. So this is what we have, and we set this equal to 0. Okay, so from the first, right, denominator dies. E to the x has nothing to do with 0, so x e to the x over x plus 1, everything squared equals 0. Just focuses on x equals 0 because e to the x equal to 0 has no solution. And denominator, when it multiplies into 0, dies. Right, when you do cross multiply. Well, I can actually do this. Oh, there we go. And all I have to worry about is the second one, which is 1 over x plus 1, let's say, equal to x plus 1 equals 0. So now 1 over x plus 1 equals to 2 over x plus 1. Should put this one on my algebra test next week. That's what they're doing now in chapter 7 or 8. How to solve this equation. It's intermediate algebra. Combine this into a single, so that's going to be x plus 1 over x equals to 2 over x plus 1. And now you have cross multiply. So 2x is equal to x plus 1 squared. Then you get to FOIL that. 2x is equal to x squared plus 2x plus 1. And then you subtract 2x, you get x squared plus 1 equals 0. No solution. Because solutions are complex. So we have a vertical asymptote at negative 1, and then we have a 0. And from negative infinity to positive infinity. Test points at negative 2, negative 1/2, and 1. And now I'm going to show the $1 million method, so you don't have to go crazy calculating everything if you have factored form. So xe to the x, x e to the x divided by negative 2 plus 1, everything squared, in parentheses 1 over negative 2 plus 1 minus 2 over negative 2 plus 1. In many cases, you can ignore a lot of stuff that you're computing. E to any value is always positive. If you have something squared, it's always positive. And you don't have to worry about those at all. You can just cross them out from the calculation. So E to A is always larger than 0. And anything squared is larger than 0. So those are always positive. Remember, I'm only looking for positive or negative sign. I don't care what the value is. I don't have to compute these things. If I can make an argument that the whole thing is positive or negative with any way, there's no reason for me to compute anything. So that's exactly what I'm going to do. This is equal to negative 2 times positive e divided by the positive denominator. So the whole outcome here is negative. Times. Now, in parentheses, when it's stuff like this, you have to compute and you will just get a number. So I have 1 minus a half is a half. Minus and minus gives me a plus. And then this is 2/3, right? No, this is 2. So that's a positive for the total of a negative, which is less than 0. And it's concave down. I don't care what the values are. Now, are you allowed to take the calculator and compute everything and get this correctly down to the 6th decimal? Yes. Right? You take your calculator, punch all of this in, and you are going to get a decimal here. If your calculator provides 12 decimals, write down 12 decimals. I don't care, right? All we care, remember what the theorem is. The theorem says, if the second derivative is less than 0, it doesn't matter if it's negative 1 or negative 1.12 or negative 7.38, right? Whatever. If it's a negative number, it's concave down. So what I did is I did analysis rather than calculation because I'm lazy. Right? I just said e to any number is positive. Because the graph for e is always above x-axis. You can't get negative y out of it, right? And then this stuff over here can't be 0. It's in the denominator, right? So whatever you have there when you square it, if you have 1, it's 1 squared is 1. If you have negative 3, positive 9, right? So whatever you have, it's always positive. So that's how I eliminated those. And then I have a negative 2. So I have a negative 2, that's a negative number. This is always positive. This is always positive. And then I computed this a little bit, just to get that it's going to be a positive value. Negative times positive is negative. Less than 0, concave down, move along with my life. Next one is negative 1/2. Use the same. So f of negative 1/2 is equal to negative 1/2 e to the negative 1/2 divided by negative 1/2 plus 1 squared. And then I have, so negative 1/2, let me see. So that's a negative 2 plus 1 minus 2 over negative 1/2 plus 1. Negative 1/2 plus 1? Yep, okay, good. I have same arguments here. I have a negative times a positive divided by a positive And then this is -1 minus a number. And I don't care what it is. So, those positives don't matter. Negative times a negative is a positive. So, larger than 0, concave up. Yay. So I have concave down, concave up. And now we compute this for 1. So f of 1 is 1, e to the 1, 1 plus 1 squared. No, it's 1 over 1 plus 1 minus 2 over 1 plus 1. Great. You just look at it and you know it's positive, right? Because everything over here is positive. These two will cancel, so positive. So another concave up. Please don't go and say, oh, I'll just alternate this, because as you can see, great.
Is that sec F?
Oh, yes, double prime, second derivative test. Should we do one more of these? Of course. You love this stuff. Problem 94. Lock the doors. No one is leaving till this is done. 2 over x cubed minus 1 over x squared. Did we have x equals 0? I thought we had vertical asymptote at -1 and x equals 0. Inflection point at x equals 0, right? Oh, -1. Okay, well, 1 was.
I thought it was vertical asymptote was -1 and then
I don't remember. Vertical asymptote at -1 and inflection point at 0. Right here. It came from the second derivative.
Oh, okay. Oh.
So we did have inflection point at 0. I never wrote the answer. This is terrible. So I'm just gonna move this down so I can write the answer. So concave down negative infinity to -1. The inflection point is not a major point. I just found a way to cheat through software. So apparently I can do this. I heard I could do it, I just never tried it before. So if I do this, if I select just the equation, I push the math button, and I pull from the menu and I say differentiate in respect to x, it tells me the answer. So I so I get to copy this in a factored form, x to the fourth. That's the first derivative. Then I turn the math off. There we go. Go away. Yeah, the magic math button, right? Then I select this, and I push math again, and I differentiate in respect to x, and it gives me the second derivative. Who would know, huh? Okay, kill that. You now set it equal to 0. X equals to 4. And we see that there's a vertical asymptote at x equals 0 from the original problem. Cool, huh? It does. It integrate solves equations and pretty much anything. Yeah, but we only work on the second derivative now. Yes, you're right. There is a critical point, so there will be a min or a max at 3, yes. So now my partition is at 0 and 4, negative infinity to positive infinity, critical points, negative 1, positive 1, and let's say 5. And now I have my second derivative for negative 1. I have 6, 4 minus negative 1 divided by negative 1 to the 5th power. So this is going to be a positive over negative, gives me a negative. So concave down. Second derivative at 1 is 6, 4 minus 1 divided by 1 to the 5th. That's a positive over positive, which is positive, which is larger than 0, concave up. And finally, second derivative at 5. It's going to be 6, 4 minus 5 over 5 to the 5. That is going to be a positive times a negative divided by a positive, which is altogether negative, less than 0. So another concave down. So now we write the answer. F of x is concave down on negative infinity to 0, union 4 to infinity. F of x is concave up on 0 to 4. Note use of parentheses because you can't be increasing, decreasing, or concave up or down at a point. So we don't use those brackets. Now you saw me earlier use brackets for a trig problem, but that's because they close the interval, right? So when they chop off the interval, then you are using the same notation at those points.
Why is it middle over out x is equal to 4?
Oh, when you cross multiply, you get 6, 4 minus x equals to 0. Then divide both sides by 6. You get 4 minus x equal to 0, and then x equals 4.
Yeah.
No, minus 4, because 4 minus minus 4 would be 8. It's not 0. It has to be 4. X has to be 4 in order for 4 minus 4 to be 0, right?
I just factored it.
X minus 4 or 4 minus x is the same. They both give you x equals 4 if you are looking for 0. Because 4 minus 4 is 4 minus 4, which is 0. So either way you get it. Now, what's the ultimate test? I know the class ended 3 minutes ago, but the ultimate test is you go graph the function. And you take a look at the graph, and you take a look at what you have. Right? So I'm just going to very quickly jump to Desmos on the main machine over here. So desmos.com, and then in the graph, I'm just going to plug in our function. So we have 2 divided by x cubed minus 1 divided by x squared. It's very hard to see. Oh, you can't see it at all. There's that. It's very hard to see. Okay, so we see up to 0, right? We see it's concave down. Do we see concave down up to 0? Now, it's very difficult to see that there's a change of cavity at 4. But this part is concave up, and then after 4 is concave down, because the graph is going up, but at a decreasing level. So it's very difficult to see, because it's just such a long graph. It's just not that friendly to see, but it's there. All right, well, that's it for this test. We'll do next 2 lectures next time, right? When is the test? Is next week sometime, right?
Monday.
Next Monday. That, yes, so we'll do 1 lecture and a review.
Monday or Wednesday? You said Monday? Yeah, I thought.
You said Monday. That means that the quizzes are starting tomorrow morning, 6 a.m. Okay, good. Yes, so we do 1 lecture and then review.